Hi everyone, and welcome to the video on section 5.1 and 5.2. These two sections are going to be what we talked about as the, what is this antiderivative idea geometrically from section 4.8. And so geometrically, I guess it's in the title, we are going to be using this antiderivative idea to think about area under a curve. And so you might not see right now how that has anything to do with derivatives, antiderivatives, but that's what these sections are about, is trying to build that idea up. So we're going to start off with just an example here. Suppose you want to find the area under this curve. So when that's said, what's implied is you have a picture. So when this is said, area under a function, the picture you should have in your head is you've got some function here, it's above the x-axis, and I want to know how much area is right here. Right? So this is two-dimensional, has an area. Unfortunately, though, this is an area like we have seen it before with kind of general geometric shapes, because those had nice formulas. Here, I don't know what the heck the formula is for this. It's got all these curvy lines. I don't know. It's not a box. I can't just do length times width. So what do we do? Well, what we're going to do is we're going to try to understand this area by taking it and breaking it up into smaller pieces. And then those smaller pieces are going to be used to try to approximate this. And what you should think is like, the only tools I have for area are things like I know the area of a rectangle, right? So this would be length times width. So I know this, right? How can I use the fact that I know areas like this to try to figure out what's happening here? And what we're going to do, this is, the kind of big idea here, is we're going to say, if I just kind of like zoom in pretty close here, so let's enhance this all the way through. If I just kind of like really zoom in here and take really small rectangles, like do you see how the top of this rectangle and then the curve here, they are too far off. Like clearly the function itself is curved there and not straight like the top of this rectangle. So I can't perfectly put this pink rectangle on top of the function and this area I want and say, look, it fits perfectly. But what you could see is that if I made these rectangles small enough, they would get closer to kind of nicely fitting in. And what I could do here is I could just try to fill this up with these rectangles. And what you'll notice is, it's pretty good maybe, but these rectangles maybe don't do a perfect job. But if I could think of just having a bunch of these rectangles that I just sit on top of this, like, yeah, okay, it's almost like I could cover this area with rectangles. And that's the idea you should be thinking about. I've got this area, but like, I don't have a formula because it's all curvy. But I know how to find the area of this rectangle here. Can I just take a bunch of these different sized ones? See, these are all different sized. Can I take a bunch of different sized rectangles and stack them on top of this area? And I can find the area of a rectangle, because length times width, easy. Can I take a bunch of them, stack them on top in such a way that, I'm pretty close? Like, it's not perfect, maybe, but it seems like these rectangles cover pretty well. And the answer to that is yes. We can do that, and that's where the antiderivative is going to come in. Again, you might not see where. That's totally fine. We'll get there, but that's the idea of this, is that we're going to try to find these areas by stacking these rectangles, which we know how to deal with, on top of that area, trying to fill it out. So let's go back to this example. We've got this function here, which I've graphed below. I'll show it to you in a second. So, okay, we've got this function. All right, and we want to know the area between x equals 1 and x equals 3. And so again, this is the picture, and just to kind of show you what we mean when we say area, just visually, I start here at x equals 1, and I'm just going to draw a line so that you see where I'm cutting. And then x equals 3 is right here, right? So I'm going to draw another line, and I'm going to go straight up here-ish. Oh, I always start curving. That's not good. Just pretend that's straight. And then again, I want the area under here, right? So, we can just kind of color this in. I want to know what this area is. So, this is not a shape that I have a formula for. It maybe kind of almost looks like a triangle-ish, but it's not complete, right? Because I kind of slice it off. And this is not a straight line, so the triangle formula won't work. So at this point, we're kind of like, oh, I don't know what to do. Well, let's keep reading and see what this says to do. So it says we can partition. What does this mean? This word mean? It just means cut it up. We can partition the interval 1 to 3 into n equal subdivisions. So that's this idea I was talking about up here. We're going to go from 1 to 3 and we're going to chop it into smaller pieces. Okay? The width of each of these subintervals we denote by delta x. X because width is this direction, x direction. Delta meaning change, so change in x. Okay, so each rectangle will have a specific width, and again, the width we are going to fix for each one of these. And we can figure out how much width is going to be there by just going, you want to go from 3 to 1, and you want to divide that into n equal divisions. So I know that sounds like a lot, but you'll see when we do an example here, it's like, oh, of course, it's what I would think. So let's say we want 4 partitions. So here's what we're going to do. Ready? We're going to say, okay, I want to know the area under here, or try to guess it. How am I going to do that? Well, I'm going to split up this here into 4 pieces, right? So if I just kind of go like this, that's 2 pieces, 1, 2. So I'm going to do it one more time, half and half. And look, now I have 1, 2, 3, 4. So this is my first, my second, my third, my fourth little subsection here. So immediately, delta x is 3 minus 1 over 4, which is 1/2. That's this width here. See, 1 to 1.5, 2 to 2.5, 2.5 to 3. So my delta x, which you can just immediately at the beginning of a problem like this calculate, is the width of each of these rectangles I'm about to build. Okay? And so here is the choice. I want to put in rectangles here. Here's my goal. I say, I know a rectangle. I know it. Its name is Steve. Just kidding. I don't know this rectangle. But I know how to find the area of a rectangle. If I can just take rectangles and try to cover this green with rectangles, I can get an idea of what the area is. Will it be perfect? No, absolutely not. It will not be perfect. But it should be pretty good. So how do I do that? How do I take this rectangle and try to put it on top of this picture so that it covers this, it could be under a little, could be over, but it's pretty good. Well, I told you what the width is, right? It's 1/2. So I don't choose that. That comes from me setting up this delta x. So I know my first rectangle is going to go from 1 to 1.5. Just immediately. I know that this blue rectangle is going to go 1 to 1.5. Okay. So the question is, how tall do I want it to be? And we have a bunch of choices. Well, somehow it should involve the function, right? I don't want it to be like 40 tall. That would make no sense. I wanted to try to get, kind of as tall as the function in some way. And so the first 2 things we're going to talk about are using left endpoints. So left endpoints, okay, and then right endpoints. So how do we use a left endpoint? Well, all that's saying is that here's my rectangle. It's going to sit right here, right? How do I figure out the height? Well, the way you figure out the height is start on the left of the rectangle. So let me highlight this so you can see what I'm saying. Start on the left of this rectangle, right here, right? And the height will be, go up to the function. That's going to be the height of my rectangle. I'll draw this over, and boom. This is my rectangle that I'm trying to fit over the green. Now, you might be like, you did a bad job because look, there's this green up here I didn't cover. Well, yeah, it's an approximation. It's not going to be that great. But you'll see how this works. So this is going to be rectangle number 1. And the pink covers up some of the green. Okay, rectangle number 2, right? Again, I know it has to have 1/2 as its base, right? 1.5 to 0.2. So this is going to be the base of my rectangle. Now again, left endpoints. So I'm focused on 1.5 to 2. What's the left? 1.5. So I start there and I go up and I hit the function. And I go over. That's my second rectangle. I covered up some of the green. Again, you're seeing here like I'm missing a chunk of it. So this approximation we're doing of the area is going to be under, right? We're under approximating, but that's okay. It's just an approximation. Let's do the next one. So I've just done 2 of these. Let's do a third one. Okay, so 0.5 again. Delta x is 0.5. That's the width. And then how far do I go up? Well, it's a left endpoint. So I start here at 2 and I go up, 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 up. I hit here and I'll make this as my next rectangle. And there we go. I'm going to count up all this area, and we'll do that in just a second. We'll count up the area together. Lastly, I've got my fourth one of these, right? My fourth rectangle. Again, delta's 0.5. All right. What's the height of this rectangle going to be? Well, left. Start at the left of this little sub-interval. Go up, 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 and make a rectangle. Okay. So, I have done what? I have taken the green area, which is what I wanted, the area under my function, and I've tried to approximate it by putting these rectangles over it to try to fill it up. Now, I didn't do a great job. I'm missing this green and this green and this green triangle, not quite a triangle, but looks like one, and this one. I'm missing those. I didn't cover them, so I'm not gonna do a perfect job on this, but it's not gonna be too bad. So, how do we actually figure out what just happened here? Well, the way we do this, and the notation for this is L for left endpoints 4. Why 4? 1, 2, 3, 4 rectangles. Hopefully that's not too bad. What we do, this is just the area. L4 is the area. How do I find the area? Well, how do you find the area of a rectangle? It's width times length. Okay, so I can do that. The width of this first one, so you're going to add up this first one here. It's 1/2 times, and then what's the height here? Oh, what's the height? Well, what did I do? I started at 1, and I went up until I hit the function. So, that's f of 1. So think about that for a second. This height of this rectangle is f of 1 because that's exactly this point. Okay, so then let's add the next rectangle. Plus, width is 1/2 times, well, what's the height of this rectangle? It's f, because I hit the function, of 1.5. Okay, keep going. Plus, third one. This is going to be 1/2 times, and then I'm going to f, because again, what's the height of this? Height, it's the function at 2. F of 2. And then lastly, I'll have this one, which is what? It's going to be 1/2, that's my width, times the height of this is f of 2.5. This sum of rectangle areas is going to be my approximate area under the curve. It is wrong, right? It's not the green. I'm underwhelming with the green, but it's not going to be too bad for such a small amount of work. Right? This is called doing left endpoints. So this is summarized in the table here. You'll see I have x, my 1, 1.5, 2, 2.5. This table goes all the way to 3, but remember, I don't use this third one, did I? No, I only used the left endpoints. This one, this one, this one, this one. But for completeness, you can see the whole table, because we're going to use the right one later. We have, what is f of that? Well, I needed f of 1 right here, right? 7. Delta x is 0.5 or 1/2. And then what do I do to find the area of each rectangle? I take the function value, that's the height, times my delta x. So how am I going to find the L4 here? L4, just using this table, is 3.5. That was my first rectangle, right? Starting at 1 was the height, plus 6.1875, plus 10.5, plus 16.8125. Okay? And again, we don't need this third one right now. We don't need this because that would be a rectangle with height f of 3, which we did not have. Just keep reminding yourself of that. We did not go all the way up to 3 to do this. Nope. We only went to 2.5 for this last one. Okay? So then we can go to a calculator to try to see what this is, and the numbers aren't too bad, so we can do this. 3.5 plus 6.1875 plus 10.5 plus 16.8125 gives me 37. So my approximate area using left endpoints and 4 rectangles is 37. Okay, we are going to learn in these next few sections how to find this exactly, which is where antiderivatives will come in. But for now, we're just going to try to use these approximation methods to kind of think about what's happening here. Okay, so last values in this column represent the area. Area. How could we use these to approximate the area? Well, we just add them up. It's the area of this, plus the area of this, plus the area of this, plus the area of this. That's it. So that's called left endpoints, and that's our approximation. Okay? So hopefully it's not too bad to see how, yep, this could work as an approximation. Whoopsies. This could work as an approximation, and yeah, it's not too bad. All right? So, okay, let's keep going. Now, let's try using right-hand rectangles. Okay, or what's commonly referred to as right endpoints. So we're going to try this again, but this time we're going to use right endpoints. And let's just stick with the same n, the same delta x. So the notation for this is R4. This is going to be the area, right, that we want to get using 4 right endpoint rectangles. So the first thing we're going to do is just recolor the actual area we want from 1 to 3. Oh, that was a slightly more straight line. Pretty good. Okay, so remember, this is the area we're after. The area under the curve. Okay, so here we go. We want this area. Well, what are we going to do? We are going to use right endpoints. So let's do this in, what would be a good color here? Let's try purple. Right endpoints. So, okay, remember how this works, right? We want to break this into 4 pieces. So again, it works the same, right? 1.5, 2, right? 2.5. So then I've got a rectangle that's going to be here, a rectangle here, another rectangle here, and then another rectangle here, right? There's 1, 2, 3, 4 rectangles. So it actually starts exactly the same. You're putting the rectangles in the same spot, so all of that's the same. What's different is how do we figure out the height? So focus on this first little rectangle here. We know its width goes from 1 to 1.5. What should its height be? Well, again, it should deal with the function, but this time take the right endpoint. Shoot up to the line, bonk, and then you find your height of your rectangle. Now, what are we noticing about this one? I've overdone it. Look, my rectangle, the area is bigger than just the green there because I overshot. And that's perfectly fine. Again, it's an approximation. So that's rectangle number 1. How do I get rectangle number 2? Well, again, it goes from 1.5 to 2. And I'm going to use a right endpoint here. Hit up the function, And again, I've overdone it, which is totally fine. What about this one? Right endpoint. Hit the function. That's your height. Okay, I'm going to pick up all this. And then finally, right endpoint. That's at 3. I'm going to go all the way up here, and boom. So there you go. I have taken rectangles, something I know how to do the area of, and I've laid those on top of my green area, right? This way I've done it so it covers, but it actually overcovers, which again, that's fine, that can happen. Okay? And this is my attempt at trying to approximate. So okay, well, what's this going to look like then? Well, it's going to look very similar, right? There's very subtle differences. The area of these purple rectangles will be what? It's a width of 1/2 times, but here's the trick. Last time it was f of 1, right? Because the height was 1. No, this time it's f of 1/2 because I used the right endpoint. That's my height. Plus 1/2 times f of 2 plus 1/2 times f of 2.5. That's this rectangle. See, it has height, f of 2.5. And then lastly, I'll have f of 3. Notice I finally used 3, right? F of 3. I didn't use that last time because it's the rightmost x value, so it's only going to show up in the right endpoints, not the left. But I left off the leftmost point because I'm doing right endpoints. So I can figure out what this is, and I have my area, my approximating area. So we've got this table here. Again, for right endpoints, I only care about these for the right endpoints. For left endpoints, I want the first 4. So I'm going to take these and add them all up. Take this and add. And we can do this pretty quick since we still have this in our calculators. So I'm going to just add all of these up. And this is going to give me 59. So my area, overshooting it, I think is 59. That's my approximation. Okay? So again, this is a rough approximation with only 4 rectangles. And how did I get the height of these rectangles? I used the function value, right? We want to get up to the function, and I used right endpoints for this. Okay, so hopefully that's not too bad to kind of think through what we're doing here. Okay, so before we get to this, I just want to make a few observational notes that hopefully when I just say this, it won't be too bad to see. How could we do this better? There's a bunch of answers to that question. But one way we could make this better is, why don't we do more rectangles? So this can get a little bit cluttered, but I just want to kind of show you on one of these rectangles what I mean. So we're going to super enhance down to one of these rectangles. Now, look at all this purple that I overdid it at, right? This is bad. We want to cut down on this extra area we picked up. Now, how could we do that? Well, one thing we could try to do is we could say, give me a larger n. Give me more rectangles. So what would it look like to do more rectangles? Well, just kind of focusing on this one rectangle, what if we were to split this in half? So turn this one rectangle into 2. Well, if I'm using right endpoints, now I have this first rectangle. I'll go up to the function, and then boom, this blue one will be my first rectangle. Okay, check this out. This first half of the big purple one, look at all this extra area I got here, right? But when I use this smaller rectangle, look, I'm not counting all this up here. I'm only counting this much smaller area above the green, right? I'm still right above here. I still have this blue here that's no good. It's too big. I'm overcounting. But look at all this extra that I was able to take away from my previous And then we, just to kind of complete this, we would draw in the second rectangle here. And you know what, I'm still picking up a good amount of this extra area, but you can see it. Look, I have now, with this blue one, cut out this entire rectangle of extra purple, just gone, which is good because that was all extra area. So just by doing that, and you can try drawing this for yourself, right? Cut this one into 2 blue, and you're going to cut a big chunk out, big chunk out, big chunk out. It's better, right? Do it again. Cut this one in half again. And you'll notice there's still a small chunk that's overdoing it, but it's smaller than before. And cut it in half again. Smaller. Cut it in half, cut it in half, cut it in half. So you might be seeing our like Calc 1 ideas kind of coming in here, right? I'm doing something, I'm letting n get bigger, n get bigger, n get bigger. More rectangles, more rectangles. What's happening with the area? Where's it getting close to? What is it approaching? Oh, there, I did it. That's the key word, right? What is this approaching as I make more and more and more rectangles? And what we'll see is that that is actually approaching the true green area. As I make the rectangle smaller, my error in my approximation gets smaller, and the closer I get to really truly finding out the green area. And of course, what's the math thing we do when we are doing a process over and over again, but we're making n bigger or we're making h smaller? Oh yeah, a limit. Of course it's a limit. So we are going to represent this as a limit, and you'll see kind of how that all comes together in just a little bit. But just to kind of give you the idea of what's going on there. So okay, more rectangles, better. Here's another way we can do this, and we're not going to go too much into this, but one other way, which hopefully is something you could look at this and be like, yeah, like this kind of makes sense. For L4, what happened? This was an underestimate, right? R4, what did we do? This was an overestimate. So if you have this process for this specific function, left was under, right was over, but hopefully you should be able to think like, yeah, I could draw a different function where those are flipped. But in any case, using this kind of idea, one is an under, one is an over, it might be not too bad to say, well, okay, well, why not just average them? L4 plus R4 over 2. Why don't we just average those two together? This itself is a separate rule that we could talk about, that actually you'll talk about in Calc 2 separately. There's actually a separate geometric shape that goes with this rule, because why am I just sticking with rectangles, right? I have other geometric shapes I can use that don't just have flat horizontal tops, which obviously stink for doing this. But that's further down. You don't have to think too much about that right now. But for now, we can try this. So what was it? 59 and 37. So let's see. So it would be 37 plus 59 over 2. Okay, so that's going to divide nicely. But we'll put it in. 37 plus 59 over 2 equals 48. So I can average those two together to try to find a new approximation. Again, this is the average of the left and right. So let's keep going and look at some of the estimates that we get by increasing both the left and right endpoints, but increasing the number of rectangles. So, okay. Down here we have a little table with 8 partitions, and again, just kind of shows you all the pieces. F of x again will be the height of the rectangle. Delta x is just going to be the fixed width, which is now different, right? 8 partitions will have half the width. So we've shrunk down the width of each rectangle, and then of course multiplying the two. So for the left-hand sum, we're not going to do the whole thing out, but I just want to remind you, for the left-hand sum, we are only using the left endpoints. We leave this right one off. So I would be adding all of these up, which will show you what that looks like in a second. With the right hand, again, we're only going to use the rightmost endpoints, which is 3 is the rightmost all the way to these. These are the ones we'd be adding up. Okay, so what that looks like, and you can go to this little applet. It's made from Mathematica, which we don't have to worry about. You don't have to use Mathematica. It's just online. You could type in our function 1 to 3, and then you can change up, do I want to use left endpoints, right endpoints, how many of these rectangles do I want, and you can see some of the numbers. So like we did, 37 and 59, left endpoints, right endpoints. As we go to 8, I go 42 and 53, so this was an underdoing it, right? So now as I do more endpoints, it gets bigger because I'm capturing more of the green. Over here, remember, the 59, we kind of way overdid it. As I go to 8, look, I've gotten smaller because I've thrown out some of that extra area. And so what we see here is that as I increase n, seems like a silly thing that I'm stressing, but this is very important. As n goes to infinity, so read down, what's happening? These are both approaching. So this one's under, and it's getting bigger and bigger and bigger and bigger. But look, it's getting bigger, but it's slowing down. Slowing down. This one, it's getting smaller, right? Because I overdid it. But it's slowing down, right? It's approaching something. These are both, as n goes to infinity, going to approach, both of these columns will approach the actual area. They'll both do it. Doesn't matter if I use left, use right, who cares? They're both going to approach the actual true area, okay? Which just happens to be 47, so that actual area, 47.33 repeating. So by 200 rectangles, I'm pretty close. And as I go out more and more and more rectangles, I'm going to get closer and closer and closer to that actual area, okay? And so, again, I mentioned this is a limit. And so we're going to deal now with some notation that might be a little bit weird, but you'll get used to. So here's the first thing. And I just want to kind of stay on this one as to not overdo it. The area, the true green area, right? So this was the area that was green before, right? That true green area that we had under our function is going to be equal to the limit as n goes to infinity. What's this n? Just n for number. Remember it that way. Number of rectangles. And there's an implication here, remember. The more rectangles, the smaller in width they are. So that's something I remember. I'm shrinking the width down. So as I let the number of rectangles that I'm putting on top of my area to cover it up, as I let those increase, the number of them, and then what I do is I calculate the area of all the rectangles. So what's this whole big crazy thing here? Well, this whole big crazy thing, just remember, is the area of the rectangles, the total area of the rectangles, where what's delta x? Well, remember, delta x was just the width. This is the width. Oh, shouldn't have done that green. I always overdo the colors. Let's do that in blue now. Blue. This is the width, okay? So delta x was the width, and then what does f of this weird x1 star thing mean? Well, that is just the height. This piece here is just the height, okay? And we're not going to prove this, but I'm just going to tell you now what's happening. The height here could be taken with right endpoints, left endpoints, or any point in between you want to do. That's what this star is representing here. This star is representing, it doesn't matter if you want to take all left endpoints. It doesn't matter if you want to take all right endpoints. It doesn't matter if you want to mix and match, if you want to take the middle point. If you just take points inside that width, plug it into the function to draw your rectangle, get the height, multiply it by the width, add up all of those. You do that, and then you let n get bigger. Do it again. N get bigger. More rectangles. More. As you let the number of rectangles go to infinity, that approximation that you're doing with just rectangles is going to approach the actual true number, which might seem a little bit crazy that that works, but hopefully looking at more of the pictures, you can see how the rectangles don't work perfectly, but as I increase the number of them, like we showed above, the error is getting smaller, and all we need is to find some way to express how do I make the error smaller, forever. What does that go towards? It goes to the actual area. So we love limits, so this is perfect, right? I'll just do a bunch of limits. No, not great. We're going to find some rules for this like we did for derivatives, don't worry. There is another notation, though, I want to just show you, and it's right here. And it looks, just give myself a little space here. It maybe looks a little bit much. But again, it's not going to be too bad. You just got to get used to it. So area, done. Equal sign. Look at us go. Easy. Limit as n goes to infinity, same thing, right? As I let the number of rectangles get bigger and bigger and bigger. What's this monster of a thing? Well, this thing here, this notation here, is all this means is sum, aka add. So this is just saying I'm going to add up a bunch of stuff. Get ready. Okay, so what am I adding up? Well, I'm going to add up this. I'm going to add up a width times a height. Cool. That's what we're doing up here, right? And all of these symbols here are just telling me how to do the addition, how to kind of count up all these things. I is an indexing variable, just kind of like a dummy variable that helps me keep count. I start at 1 because, yep, I want my first rectangle. And then I keep adding 2, 3, 4, all the way until I hit my nth rectangle, where in the case above that was 4, right? So it would be rectangle 1 plus 2 plus 3, and then I would hit 4 and I would say, okay, I'm done adding. So this notation just means start at 1 and keep adding until you get to n, which in our specific case before was 4. But what this is telling us is let n go to infinity, right? So add up the areas when n is 1. One big rectangle. Boo, it's terrible. When n is 2, 2 pretty big rectangles. No, not going to do a good job. Try 3. Add up all the areas. Try 4. Do it again. Try 5. Try 6. Try 7. See what's happening with those areas that we're adding up. And if that list of numbers is getting closer and closer to something, that something is going to truly be the real area. So a little bit scary maybe of notation, but it just means these say the exact same thing. This sum notation is just important to get used to. You will use it in Calc 2 as well. And the other thing is this notation will be replaced in just a minute with some very similar looking notation, which is going to be very important for us going forward. So the area is your approximation with rectangles. Just let the rectangles go to infinity. Let the number of them go to infinity. And once you've done that, you found the area. So how the heck do we do this? Well, we don't do this, luckily. What we do is we go to section 5.2, bring this up, and we define something called the definite integral. This is going to be your life in Calc 2, so buckle up. So we're going to define this thing called the definite integral, and here's all we're going to do. We're going to take this scary thing here that we had just defined, this limit with the sum, add up all the rectangles, and we're going to call it this thing. The definite integral of a function, f of x, from a to b is this crazy limit that we had done. That's it. We're just giving it a fancy name. See this sum that we just talked about, this area of rectangles that we're adding up, but we're letting the number of rectangles get bigger, 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 and seeing what happens? This is called an integral, a definite integral. We're just giving it a fancy name. So this whole big crazy thing here is just us giving a fancy name to this limit of areas of rectangles that we had added up. That's it. So this is a fancy name for this. That's it. It's an integral. Okay? So we've got this fancy name now, and you can read through here, but all of these are just what we had talked about. You're going from a to b, which for us was 1 to 3. You get your width. You take points inside each rectangle width that you want. You could do left, right endpoints, whatever. You then do this process where you width times height, add them all together. That's your approximate area. Now let n get bigger. Try with more rectangles, more rectangles, more rectangles. What's happening there? This is called a definite integral. And what we're about to do is we're going to make this connection here in a little bit, where we have this amazing theorem that tells us how to calculate this without doing this crazy thing and a limit. It's going to be so good. It's going to be like the first time you saw derivative rules, where you're like, wait, I can do a derivative without a limit? That's what we're going towards. But we have a special name called a definite integral. Okay? And this, just notation-wise, this Riemann sum is a limit of Riemann sums. This is the fancy name for this here. So let me color code this just so we are aware of it. So this Riemann sum here is the fancy name for this sum. So it's named after a famous mathematician who, was doing this. But this is it. Definite integral. If you see an integral sign going forward, oh, I know what that is. It's just this limit, because it's area under the curve, right? So I know how, what that is. It's going to be the limit of these approximate rectangle areas that I had done. That's the whole thing, okay? So, all right, there's some, interesting information here, some history you can read through, okay? A couple pieces here to think about. One, this is a number, right? It's you need to make the connection just geometrically with this being an area, right? It can not be an area exactly. We'll see some examples of that. But just to start, you think of it as like an area under the curve. So if you give me an a, b, and a function, and I can draw the picture and color code the area, well, that's just a number. It's the area, okay? So when you're viewing this here, you should be thinking, yes, just an area, just an area. We will use different notation. Sometimes we have functions defined on x, but you guys have seen this. Sometimes we have functions defined on other variables like theta or time. And so we can do this same idea just with different variables. So that's fine, okay? All right. You just have to be careful with this area thing, and it's explained here, because it does not mean area all the time. And so there's a little caveat where we have to think about this picture. And so, you could focus on either of these pictures. But here's the idea. Let's say we have this picture to the right, and we want to do the same idea, right? I want to find the area under this curve. Clearly there's area here and there's some area here, right? Okay. Well, how would we do this? Well, let's just do what we would do. We would split this into our little petitioned up area here, and we would put rectangles in, right? We got some rectangles. Here they go. And we're doing all this. But here's the problem. Like, okay, we're putting these rectangles in. And then remember, we're adding up the area. So this would be delta x times the height, f of x1. Okay? So I guess we're doing right endpoints, but you get the idea. Here's the problem. This is a negative number. F of this x1 here is a negative number. So when I multiply these, I'm going to get a negative number. So that's not good because area is positive. So when we do this definite integral, we have to remember that geometrically we can think of it kind of like area, but if you have a function that dips under the axis and takes on negative values, when you do this area idea calculation and you do the limit, you're going to be picking up negative here. From this point to this point, that definite integral will be picking up negative value. Here to here, a to this, it's going to be positive. It'll perfectly represent area. Here to here, it's going to represent area, but it's going to look like negative the true area. Just because of the way we define this, right? We're plugging into the function, but the function is negative. So this height here is actually a negative number. And then from here to here, it's again going to pick up the true actual positive area. So just be a little careful. I don't think there's any issue with you looking at this integral and going area under the curve, as long as you remember that if the function dips below the axis, it's not truly representing area, right? It's going to be picking up negative. So that's going to throw off the idea of area. You just have to pay attention, okay? So, there's lots of ways. If you really wanted to know the true area here, total area, then we have ways of dealing with that where you just do the definite integral only on this little section, put that to the side. You do the definite integral here, but you slap it with a negative, right? Because negative would be positive. Take that number, and then you do the definite integral from this point to b. And you add all those three up, and you could get the true area. So I know that's a little tricky, but just remember, you're thinking about these ideas, go back to this way we defined it. Width times the height of the rectangle will be the function value, but the function value is negative, so you got to be thinking about that. Okay, and so there's a lot of things like this we need to think about. So lots of properties. Okay, so these are just properties you're going to have to try to remember. You can go back to the definition with the limit of the adding up the rectangles to kind of do all of this, and that's totally fine. Okay, but there's a couple of different things here to remember. So one of the properties is thinking about this definite integral. We do not have to always go from a smaller to b bigger, okay? Most of the time when you look at this and you set them up, you want to set it up that way because then it naturally kind of fits with everything we're thinking with area and all that stuff. But it does not have to be that way, okay? So what ends up happening if you, instead of going a to b, where again a is less than b, so just as an example, like 1 to 3, f of x dx. So instead of this, I could calculate this 3 to 1, and it's me going backwards. Which, why do I say backwards? We're so used to going, and I've helped train you on this. You go from left and then you go to the right. When you're doing derivatives, right? We're always looking that way along the x. This is kind of what's, how we define things. But this integral is actually going the other way, right? Instead of 1 to 3, we're going 3 to 1. So that would be going the other direction. And what that ends up doing, if you work through the definition, is that ends up just popping out a negative. So if I do this antiderivative from 1 to 3 of some function like, like here, then I could, just do the limit, do everything, get the area, we're all good. But if instead I wanted to do the definite integral from 3 to 1, we always write the starting number where we want to start on the bottom, ending number on top, then that'll actually pick up the negative of that. So just something, this is actually this is a pretty useful tool. So just remember, if I'm going from A to B and this is smaller than this, then I'm all good, don't have to worry about it. But if I flip the two, that just puts a negative on the value of the definite integral. So something to remember. Another one, what if A equals B? So what if I want to take the integral from -1 to -1 of some function? Okay, just think about it. Think about the picture. Draw yourself a little picture here. Here's -1 and here's my function. So there it is, around -1. I'm trying to find the area under something, right? So okay, I want to find the area between -1 and -1. So here's my function, drawing a rectangle. I'll wait. Oh, you can't draw it in because there's no width? Yes, exactly. There's no width here. So there's no area at all because I can't draw in a rectangle here. So I'm not adding anything up. 0. Immediately. If you go from A to A, -1 to -1, 2 to 2, whatever numbers you want to pick, but it's A to A, the two bounds here are equal, you're not adding up any area because you haven't moved. There's no rectangle you can fit in there. So that's 0. Another very useful identity. Okay? But again, it just goes back to thinking about it as how we defined it, as this area idea. And then this falls out pretty quickly. Okay? There are some other really, really, really nice ones. If I want to do the definite integral of two functions added, I can do them separately, which is a similar rule to what we had with antiderivatives and derivatives, right? And limits, so hopefully that's not too bad. There's the I can take the constant out rule. That's awesome. Subtraction breaks up over subtraction, okay? Number 5 is a really, really important one here. This might look kind of nonsensical when you're first looking at it, but you got to pay attention to the bounds. This one, very, very important for us, says if I want to do an or I shouldn't say that yet, we haven't talked about that. If I want to do the definite integral from a to b of some function, here's my function, woohoo! What I could do instead, which you might say like, why? We'll see some, ideas in the next couple sections why you might want to do this. Instead of doing this whole big area, which we'll kind of color in green here, instead of this whole big area, I could instead calculate first just this purple area, A to C, and then I could add to that this, let's do red area, from C to B. That's going to fill up the whole area. So I can take these indefinite integrals and I can break them into pieces if I need to. Remember before how I said, oops, sometimes the function can go under the axis and then, the area's weird? We can deal with that by just breaking the original integral into pieces, integrating regularly the positive pieces, and you're all good, and then every negative chunk, just slap it with a negative. This allows us to do that, to break us into pieces. So this is a really good one. But these rules also are all very, very helpful for us when trying to do these definite integrals with more complicated functions. I can add two functions and I'm all good. I can break things up, subtract, multiply by a constant, just pull the constant out like we're used to. So good stuff. And so I know this was a lot, but this kind of summarizes, the 5.1 and 5.2 idea. And so what we'll be working on the last couple sections of this class is, can we find some rules, an easier way to calculate these definite integrals, finding these areas under the curve. And this is where the big connection in calculus happens. So just to give you an idea real quick, what we're going to end up seeing is that we can take the antiderivative of this function, use that and these two inputs to find the total area. And as something for you to just try to chew on if you want to before we get to those sections, you can just ignore this until we get there now. If you like that connection with, that physicsy idea with speed and acceleration and all that stuff, right? Here's the idea. If I want to know how far I've gone in my car or on my run, right, between 0 seconds and, or 0 hours and 2 hours. So I'm starting off my drive at t = 0 and then I'm ending 2 hours later, right? Okay, I want to know how far I've gone between those. What I can do is I can take my speed here, which can be defined at any time, right? I can always look down and see how fast I'm going. I can just, don't do that, right? A lot. Look at the road. But you could always know that you could find the speed at any time period. What ends up happening here is we can do this idea of adding up how fast you're going, through that entire time period, and that will end up giving you the distance you've traveled. And the connection here, the calculus connection here, right, is that speed, right, is the derivative of distance. So the derivative of distance is speed, aka the antiderivative of speed is distance. So in order to get to learn about one of these things, I can use the other. And this is the connection that we're going to kind of nail down in these last two sections. If you know how I'm changing over some time period, right, I can add that up, which aka is the definite integral, right? That's adding up something. That's what this symbol's trying to make us think about. It's just like adding. I can add up that speed, and if I do that over a time period, I'll know how far I've gone. And that's the true power and connection here, is this kind of little idea. So we'll get to this and define it better than just this example and all that, but you know, this can start rattling around your head until you start working on those sections. So check these problems out, go through some of these. Just, you have to think about the ideas. That's really the most you have to do with these sections, is just try to sit and think about these ideas. Especially, like, really the idea, just to scroll up here a little bit more that you got to get in. The idea you really want to get in is this one here, where you gotta convince yourself that I could get the area under any of these curves, no matter how kind of crazy looking they might be, by just trying to fit these rectangles under them, adding up the area of the rectangles, and then realizing that the more rectangles I do, the better that's going to get. That in turn naturally should be a limit, and now I'm in calculus because I've got this limit happening. All right, and that's what you want to really wrap your head around, because that construction is going to happen in Calc 2 as well. You're going to be like, oh, I'm so done with limits. I've got integrals. I've got derivatives. Ha ha ha. Nope. You're going to do something new, which is going to use limits again, because the construction will be, well, take something small, figure that out. Ooh, add it up a bunch. Oh, do it more and more and more. Limit. So you're not out of the woods with these limits. It's going to happen again in Calc 2 and again in Calc 3, because it's basically the foundation of calculus. So just start really grinding the gears with this idea. Of course, any questions, let me know, and I'll see you in the next video.